This is part 4 of our review of the first semester in tensor calculus. I want to look at an example that's very simple. Firstly, think of two vectors, u and v. U is going to be 3 plus 2j, and v is going to be 2I plus 5j. Since these are Cartesian coordinates, the dot product is easy to calculate. 3 times 2 plus 2 times 5 works out to be 16. Remember that number, 16. Now, on the other hand, I can get formulas that express the components of a vector in polar by using our standard formulas. All of those partial derivatives that we looked at previously can be used to figure out that the r component of a vector w is cosine theta times the x component plus sine theta times the y component. Likewise, the theta component of a vector is negative sine theta over r times the x component plus cosine theta over r times the y component. The metric in polar coordinates has components 1, 0, 0, r squared, meaning that the way I calculate the dot product is 1 times the product of the r components plus 0 times the r component of u times the theta component of v plus 0 times the theta component of u times the r component of v plus r squared times the product of the theta components of u and v. I'm going to pick a point in polar coordinates that has r equal to 2 and theta equal pi over 4. If you sit down and calculate all the components involved, you can find the components of u and v in polar using the preceding formulas. I'll let the interested reader or viewer look at that. Having done so, when I do the dot product, only the product of the r components and product of the theta components amount to anything. If you grind through the arithmetic, when the dust finally settles, you get 16 for an answer, just like you ought to. Now, of course, that could have just been luck. I could have carefully rigged the numbers so that just by some bizarre coincidence you got 16, but in point of fact, it isn't. Pick some other point, Q, which has some r coordinate and some theta coordinate. Figure out the components of u and v in terms of the polar basis, not at point P, but at point Q. Writing out the terms that matter, you'll notice that I have two factors of r here. Within this bracket, each term has one factor of r, likewise here. So I can think of taking one of these r's and grouping it with this factor, this r grouping it with the other factor, and the r's all cancel out. In the remaining part of this little calculation, I'm going to abbreviate C for cosine theta and S for sine theta. At point Q, the dot product is going to be this quantity. So I just have to do a little bit of algebra now. Multiplying everything out and canceling things that will cancel out, I find out in the end the dot product is 16 cosine squared theta plus 16 sine squared theta, which is 16, just like it's supposed to be. Now again, I could have rigged it up for this special pair of vectors so that this always happens, but in point of fact, I didn't. I just picked that point to be completely arbitrary. You can pick the components of the vectors to be arbitrary, and it turns out that this 100 r² procedure really does produce the correct dot product. Once you take into account the fact that the components of the vectors depend on position now, I want to talk about arc length. I'm going to think still in terms of polar coordinates of having some pathway in the plane. R is some function of a parameter, lambda. Theta is also. I'm going to start at some particular lambda value, end at some other lambda value, and I'd like to calculate the arc length. We're going to use the same trick that we used back in second semester calculus. We're going to chop the path up into many small pieces. We're going to chop it up into such small pieces that I can more or less treat the components of the metric as though they were constants on each little bit. Each bit of the path is nearly straight. We're going to figure the lengths of each little bit. We're going to add them up. We're going to take the limit, turn it into an integral. The length of chunk number I is the length of the vector that starts at the start of chunk number I and stops at the end of chunk number I. We can find the square of that length by doing the dot product of that little vector with itself. We know how to do dot products, so it's no problem at all to see that the square of the distance that goes with chunk number I is this combination of metric and vector components. We add up all such things. We do have a problem though. This doesn't look to be quite the correct format as an integral with respect to lambda. So I'm going to take this formula, I'm going to divide the two delta x factors by delta lambda factors, multiply by delta lambda squared, then take the square root of all of that. If I'm in 2 or 3-dimensional Euclidean geometry, this is going to be literally the distance that goes with chunk number I. If I'm doing special relativity, depending on how I do my signs, the quantity underneath the square root might be negative, so I might have to take an absolute value. For now, we'll look at the simple case. It's worth mentioning that people will often write this as some sort of symbolic representation for that. That's the same sort of ugly notation you used back in Calculus 2 when you used dx and dy as though they were numbers, even though they're not. That is to say, if someone walked up to you and said, I have coordinates u and v, and then they write this down, you could write this kind of symmetrically in terms of the du dv. 6 du dv is 3 du dv plus 3 dv du. When people write this kind of stuff, it's a shorthand for the components of the metric tensor are these coefficients. 1 plus u squared plus v squared, 3 times du dv, I'll put a 3 there, 3 there, 1 plus cosine squared u times v. In the first semester, we observed that the covariant derivative of the metric tensor has to be 0. After that, a long, tricky argument led us to this formula for the Christoffel symbols. The G alpha sigma with the indexes in the upstairs position are the numbers that are in the inverse matrix to the matrix of metric coefficients with the indexes in the downstairs position, assuming that we're working with a coordinate basis. So all of the things I need to calculate covariant derivatives now, I can get my hands on. If I have coordinates and I know the metric in terms of those coordinates, I have that complicated formula that lets me calculate the Christoffel symbols, and that tells me everything I need to know in order to calculate the covariant derivatives. In third semester calculus, you had an idea called the directional derivative. You had some function f that depends only on the location within the space. You think of traveling along some curve from some specific point to a specific ending point. As you travel along the curve, you encounter different points of the plane, different function values to go with them, and what you figured out was that the rate of change of function with respect to the parameter as you travel along the curve was a dot product of the gradient of f with derivative of r with respect to lambda, where r is the position. If lambda were time, if lambda were time, dr d lambda would be the velocity vector. Also, it's worth mentioning the word vector here is in quotation marks because we've since discovered that quantity gradient f is not actually a vector quantity but a one form instead. So if we use our fancy index gradient symbol, we can write that the derivative of f with respect to lambda is the alpha component of the covariant derivative of f times the rate of change of x alpha with respect to lambda. And of course, we are doing a summation over the alpha. I now want to think about the same thing, except I'm not going to have a scalar field defined on my space. I'm going to have a vector field. Every point in the plane is going to have a vector to go with it. I'm going to think of traveling along some specific pathway and looking at how not the scalar function, but the vector function changes as I travel along the curve. As usual, the chain rule is true. The derivative of v with respect to lambda is the partial of v with respect to x mu times the derivative of x mu with respect to lambda. The summation over mu is implied. The numbers dx mu d lambda are components of a tangent vector to the path. If we rearrange this in the usual way, I can write this as the covariant derivative component gamma mu of v times e gamma, summing over gamma, times dx mu d lambda, the sum over mu. If I wanted to, I could write this as the gamma kappa component of the covariant derivative of v, e gamma dx kappa d lambda. In one of the other video lectures, I asked, do the gamma kappa components of the covariant derivative of a vector, do those form the components of a 1-1 vector? I'm not going to answer that question, so we'll look ahead. In Calculus 3, depending on what the parameter is, dr d lambda might be the velocity vector, or it might not. As long as dr d lambda isn't 0, you can divide it by its length and get the unit tangent vector. In special relativity, this will happen almost automatically if we choose the parameter the correct way. If an individual is moving along some world line, either at a uniform speed relative to whatever frame we're using, or using a momentarily co-moving reference frame, then the derivative of the four-dimensional location with respect to proper time is automatically going to have components 1, 0, 0, 0 at each point along the world line. Because the basis vectors are changing, though, the 1, 0, 0, 0 at point P and the 1, 0, 0, 0 at point Q are not the same vector necessarily. We do know, because dot products are invariant, that the dot product of the 4 velocity with itself is going to be -1 times that number plus 1 times 0 squared plus 1 times 0 squared plus 1 times 0 squared. In special relativity, we'll be willing to call this a unit vector, even though the dot product comes up -1. The 4 velocity plays the role of the unit tangent vector from calculus 3. If you had a straight line, the unit tangent vector, firstly, obviously, always has length 1. Secondly, its direction never changes. So if you look at the derivative of the unit tangent vector with respect to proper time for convenience, say, then it never changes direction, it never changes length. In general, if the derivative of the unit tangent vector isn't 0, then at least some of its components would not be 0, and this would mean that you would have curvature of the path. For generality, I'll just use some general parameter. Maybe it's time, maybe it's proper time. In the end, it isn't going to matter. Suppose that the derivative of, suppose suppose that the directional derivative of vector v in the direction of v never changes. We figured out the formula that has to be true. This must be so. This is basically the chain rule once again, and the directional derivative formula. We know what to do about the alpha beta component of the directional derivative of v, covariant derivative of v. That's v alpha semicolon beta. V beta is dx beta d lambda. So if you write out all of this stuff and then write in what we know v alpha semicolon beta to be, you can find out that if the direction vector, the tangent vector, is unchanging as we move in the direction pointed to by the tangent vector, then this formula must be true. The first term has two the first term has two factors in it, but by using the chain rule, we can combine them into the derivative with respect to lambda of component number alpha of v, but the component number alpha of v is the derivative of x number alpha with respect to lambda, that is. So this term is the second derivative of x alpha with respect to lambda, and therefore we get the equations for straight lines to be these differential equations. Notice that if you were using Cartesian coordinates, the components of the metric are all constants, the Christoffel symbols would all be 0, and this differential equation would just say the second derivative of x alpha with respect to lambda is 0. That would mean that each x alpha is a linear function of the parameter, and you would have straight lines just like you think you should. We're going to call paths that obey this equation geodesics. When we go finally to curved spaces, we'll have this same formula, which will then tell us a wide variety of things. Even now, we can see how this is going to go. If I know the components of the metric for a given coordinate system, I'll calculate the Christoffel symbols, I'll form these differential equations, hopefully I'll be able to solve them some way, and this will tell me what the straightest possible paths are going to look like without ever referring necessarily to any Cartesian coordinates, which is what we want. There's several ways to see the symmetry of the Christoffel symbols. Since we have this formula for the Christoffels in terms of the metric, it might as well be used to calculate not only gamma alpha mu nu, but gamma alpha nu mu. The second one is the same thing as the first one, except wherever you see mu in the first one, write nu in the second one, and vice versa. If you look at the terms that I put Roman numerals above, term number 1 is the same as term number 5 because the metric is symmetric. Term number 2 is term number 4, and term number 3 is term number 6. So just directly you can see that gamma alpha mu nu and gamma alpha nu mu are always going to be the same for coordinate bases. What that means is I don't have to calculate all of these things because some of them are equal to some of the other ones. If you want to be literal about it, we'll do polar coordinates. The inverse to 100 r squared is 1001 over r squared. The fact that the metric, either in its lower or upper configurations, is diagonal means a lot of these terms are going to be 0. For example, if I want to calculate gamma 111, this is 1/2 g1 sigma. Downstairs I'll have 1 comma sigma at the end, and the indexes on the other two terms are got by cyclic rotations here. Because g is diagonal, the only terms that are going to amount to anything is when 1 and sigma are the same thing. This works out to be 1/2 times 1 times the derivative of g11 with respect to 1 plus that minus that, but g11 is a constant, so its derivative is 0. So this tells me that gamma 111 is 0. Next, I could calculate gamma 112, making the comment that as soon as I know that, I also know gamma 121. It's the same argument, except 1, 2 are going to be the indexes on the G down at the end instead of 1, 1. This works out to be 0 as well. Lastly, for Lastly, for the Christoffels that have a 1 in the upstairs position, we have to look at gamma 122, which, when the dust finally settles, ends up being the negative of the r coordinate. So we now know half of the Christoffel symbols. We know all of them that have a 1 in the upstairs position. A similar calculation reveals that of all the Christoffel symbols that have a 2 in the upstairs position, only gamma 212 and gamma 221 are different from 0. These numbers are both equal to 1 over r. Thinking of the geodesic equation for x1, I have to write down all terms that have a 1 upstairs on the Christoffel symbols. Luckily, though, only one of those is different from 0, the one that goes with d theta d lambda. So one of my two differential equations is going to be the second derivative of r with respect to lambda minus r times the square of d theta d lambda has to equal 0. writing out the corresponding equation for theta and putting in the fact that I know all the non-zero Christoffel symbols, it turns out that second derivative of theta with respect to lambda plus 2 over r times dr d lambda d theta d lambda is the other geodesic differential equation. What follows is a great deal of calculus using chain rules. I'm just going to talk very quickly about this. If you take the second equation and multiply it by r squared, you see that you can write it as an exact differential, as they used to say. This tells me that r squared d theta d lambda must be a constant, which I'm going to call h. If lambda were time, this would be the angular momentum per unit mass. If I use the fact that r squared d theta d lambda h, if I use the fact that r squared r squared d theta d lambda equals h, then d theta d lambda must be h over r squared. If I put that into the other differential equation, I get this, which simplifies the second derivative of r with respect to the parameter minus h squared over r cubed must be 0. Again, there's a huge amount of manipulating to use, but basically what we're going to do is we're going to rewrite that last differential equation using two different ideas. Idea number one is I'm going to express all derivatives in terms of differentiating with respect to theta instead of lambda. Then also, I'm going to express the differential equation in terms of a variable u. The dependent variable u is going to be 1 over r. So using the chain rule and the fact that we know about the angular momentum per unit mass, I can rearrange my equation until it looks like this, which is very bad looking. At least I can divide the h squared out and get rid of it. The other thing I have to do is to express the differential equation in terms of not r, but u instead. So more chain rule, more product rule, more rearranging, and it's just beginning to look horrifically awful. But then an unexpected miracle happens. The differential equation is second derivative of u with respect to theta plus u equals 0, and that's easy enough to solve in closed form. U is some constant a times cosine theta plus some other constant b times sine theta. Now, I want to emphasize something here. We're working in polar coordinates, so we are still in the flat two-dimensional Euclidean plane for sure, but we have figured out the equations of straightest possible paths without ever talking about Cartesian coordinates. The straightest possible paths are the paths that obey these equations. If we suddenly have an epiphany and remember that we're in the two-dimensional plane, in polar coordinates, x is our cosine theta and y is our sine theta. So I could write x and y in terms of theta and have parametric equations that give me the Cartesian coordinates. If you look at what x and y are, they strongly resemble parts of the top and the bottom the bottom of the formula for r. If you were to multiply x by a, the top would be a cosine theta. If you were to multiply y by b, the top would be b sine theta. So ax plus by, after simplifying, is 1, and these are equations of straight lines in the xy plane. In the next video, we're going to look at a qualitative and quantitative way of telling if we're in a flat space or not. This is going to be the jumping off point for our curved spaces and curved spacetimes. I hope everyone is doing well. I will talk to you again soon. Stay safe.